Yeah, we have, yeah, it's just 11 a.m. here in the West Coast now. So we can go ahead and start now.
We are recording.
Yes, welcome to the Astrocheminar. I'm joining in from my home in the Bay Area. Our two speakers, Professor Ralph Kaiser and Dr. Yukiko Yarnal, are joining in from Hawaii and Goddard Space Flight Center today. We welcome you to the Astrocheminar, and this is I think the 7th of this series. We will have two talks today. First up will be Dr. Yukiko Yarnal, and then it will be Professor Ralph Kaiser. First up is Dr. Yuki Yarnal. Yuki is a NASA postdoctoral program fellow in Cosmic Ice Laboratory at NASA Goddard. She uses infrared and mass spectrometers, quartz crystal microbalance, and laser interferometry to study ices prepared under vacuum at low temperatures. During her PhD research at George Mason University, Yuki examined the reaction chemistry of molecules present on Titan and Pluto, and was an NSF-funded visiting researcher at Hokkaido University, studying chemical desorption to explain the abundance of gaseous methanol in molecular clouds. Currently, she is measuring IR intensities, optical constants, and other properties of solar system and interstellar compounds. Today, Yuki will at low temperature. So when you are ready, Yuki, please go ahead. Oh, before I go, let me remind you to please use the chat, not the chat, sorry, the Q&A button to write your questions down towards the end of the talk, and I will read the questions to the speakers, and the speakers will answer. So use the Q&A button. Thank you.
Okay, thank you. I want to thank the organizers for giving me this opportunity and to thank my wonderful colleagues in the Cosmic Ice Laboratory. My presentation is about the optical properties and sublimation behavior of ammonium cyanide at low temperatures. Comets are leftovers of solar nebula containing the initial material of our solar system. We have studied comets to understand how our solar system developed, including finding the origin of life. We have observed molecules in coma, and some compounds are directly sublimated from nucleus, but some are formed in the coma by reaction or dissociation. Water is the main component in coma, but small hydrocarbons, alcohols, acids, and bases, like hydrogen cyanide, HCN, and ammonia, NH3, are also present in the coma. In 2020, Outwich questioned the higher abundance of NH3 relative to H2O when comets are close to the sun, even though NH3 has a lower sublimation temperature than H2O. And they also pointed out that NH3 may be present in a different chemical form in the nucleus. This is the in situ analysis of 67P Churyumov-Gerasimenko. The European Space Agency sent a spacecraft Rosetta to this comet in 2004. In 2014, Rosetta released a probe called Philae to analyze the surface of the nucleus. This figure is an average spectrum of 67P reported by Laponi et al. 2020. Several peaks were identified in this 2.8 to 3.6 micrometer range, which overlaps a broad peak from the OH stretching mode of water. Ammonium NH4 NH4 plus was assigned to the 3.1 micrometer peak in the red circle in the figure. Therefore, cometary NH3 gas may originate from ammoniated salt on the nucleus. We know ammonia cyanide, NH4CN, is a salt that is formed by the acid-base reaction of HCN and NH3 on Earth's environment. Since NH3 and HCN have been identified in comets, ammonia cyanide may be one of the ammoniated salt on their nuclei. So we should be observing NH4 plus and CN minus in cometary ice. Furthermore, these acid-base reactions have been already known to occur at cometary temperature. Delakinis et al. In 2004 confirmed the production of NH4CN from the acid-base reaction of NH3 and HCN at low temperature. The second spectrum at the black arrow shows their result of co-deposition of the two gases onto an 18 Kelvin substrate, while the top spectra, red arrow, shows crystalline NH4CN, and the bottom two spectra show amorphous NH3 and HCN. Even though unreacted reactants, NH3 and HCN peaks were still observed in the blue circle, we can see the production of ammonium cyanide by the spectrum analysis in the red box. Therefore, ammonium cyanide is probably present on the comet's nuclei. Ammonium cyanide is not commercially available, so our research group prepared crystalline ammonium cyanide in interstellar conditions, measured the IR spectra, and determined IR optical properties and sublimation behavior to better interpret the observation of comets. Here are the properties that we have determined at the left column, and in the right column are examples of some applications. These properties can be used for quantitative analysis using IR spectrum and to support evidence of the ammoniated salt on the nucleus of comets. From now, I am going to talk about the system and procedures we used for determining these properties. We used two vacuum systems to prepare a sample by vapor phase co-deposition onto cold substrate in the center of the stainless vacuum chamber. The first system was used for determining refractive indices, densities, enthalpy of sublimation, and vapor pressures of crystalline ammonium cyanide. Here are the diagram and the picture of the system. NH3 and HCN came through each line, A and B, into the chamber. A gold mirror substrate on a QCM, quartz crystal microbalance, held the ice samples and was used for measuring QCM frequencies. And there are two 670 nanometer lasers with different incident angles, these red and black arrows, for measuring interference fringes during sample growth. After the salt sample was prepared, reflection IR spectrum was measured. The left figure is a diagram of vapor phase co-deposition with two lasers for measuring interference fringes. The right figure shows the result of the fringes, voltage against deposition time, and this T1 and T2 are the fringe periods from each laser. The refractive indices, eye thicknesses, and densities were calculated with knowing these T1 and T2 and the number of fringes and QCM frequencies at deposition temperature 125 Kelvin. After the sample was prepared, reflection IR spectrum was obtained to check the purity of the sample. Then the sample was cooled to 120 Kelvin, and then we measured the QCM frequencies while it was warmed until the sample was sublimed. The figure on the right shows that frequency F is with salt and F not without salt at temperature. The difference of frequency between F and F not is related to the mass of the sample on the substrate. We measure vapor pressures and enthalpy of sublimation using the difference in QCM frequencies. The top line of this table shows the result of reflective index and densities of crystalline ammonium cyanide. These properties were used to measure eye thickness and other physical properties. The following lines show additional information of amorphous and crystalline HCN and NH3 that we measured in this work. Here are the results of vapor pressure from listed temperatures and enthalpy of sublimation. The vapor pressure's uncertainties are about 5%. This is a second system for determining absorbance coefficient alpha prime, band strength A prime, and then optical constant N and K. This system is like the first system, except only one 670 nanometer laser was used for determining eye thickness. The IR transparent cesium iodide was used as a substrate for obtaining transmission IR spectrum. The figure shows the transmittance IR spectra of the crystalline ammonium cyanide with different eye thickness. The strong peak from CN at 2093 wave number and NH4 plus at 1436 wave number were measured. And also overtone was observed around 4100 wave number. The left figure shows the selected spectra of the NH4 plus band with different eye thickness. We measured band area for plotting natural log of 10 times band area against eye thickness, showing on the right graph. Band strength A prime was determined applying Beer's law using the slope with the density that we measured. Absorption coefficient alpha prime were also determined the same manner. This table shows the IR intensity of crystalline ammonium cyanide and literature values. In this work, IR intensity was directly measured by applying Beer's law to salt samples with known ice thickness. But the literature value were measured indirectly by scaling to the band of other molecules. So our results are more accurate as they are direct measurements. These are the results of optical constants, N and K. Optical constants were calculated by Kramer's cloning method using the transmittance IR spectrum with eye thickness and refractive index. Now the open source optical constant calculation program is available from Gelatinous and Hudson 2020. Then N and K are useful constant that we can produce an artificial spectrum. In summary, we prepared crystalline ammonium cyanide at 125 Kelvin for determining IR optical properties and sublimation behavior. These results will support the better interpretation of the data from observational study of comets, which includes answering the question about the abundance of NH3 when comets reach the sun. Furthermore, they can be used for quantification of ammonium cyanide in the interstellar medium. Optical constant will be seen on our website, and the future work will be using other salts and do irradiation chemistry. And I want to thank the funders and my nice Cosmic Eyes Laboratory team members. ありがとうございます。Thank you. And I will take questions.
Thank you, Yukio. That was very nice. I have one question that has come through the Q&A box. Did you include any UV or radio spectra in generating the optical constants?
No, just the mid and near IR range. Is it? Am I answer the question?
Say that again. UV or radio spectra. You said only mid IR.
Just the mid and near IR.
Okay. Got it. Also, Miles Edward says also great work. Optical constants are neglected. Do we have any more questions? I had a question about how, since these are formed, the ammonium cyanide is formed. What would be a destruction process? Is it just going to be dissociation back to HCN, or is it going to stay around to react with other things?
When increasing the temperature of the sample, then they are going to dissociate HCN and NH3.
I see.
There is no
at what temperature roughly?
So they are going to the salt going to sublimate around 130 Kelvin, something like that, and then complete sublimed at 155 Kelvin using so yeah, while increasing temperature, the salt is going to dissociate.
Okay. Professor David Nesbitt has a question, and we're going to unmute him, and he can ask the question.
Mm-hmm. Yeah, very nice. Thank you. I was wondering, I noticed that your indices of refraction for your ammonium cyanide were, it seemed in general just a little bit larger than some of the previous measurements. And I'm wondering whether or not that is just a statement that you are generating sort of a film which is closer to the crystalline solid more than was done previously. Because basically, as you generate this, there's a tendency for the material to not be crystalline, but to tend to be sort of porous. And that would tend to lower the index of refraction. So is there something that that your experiments are just basically generating better samples?
Say something.
Yeah, I think we made a good sample.
Well, I'm just trying to provide an explanation for why your numbers might be a little higher in terms of index of refraction than previously measured. Just providing an opportunity to explain why.
Because other measurement are in. You talk about the
If you'd like to go back to your slide that showed the indices of refraction, maybe that would help explain my question, right? Yeah, there you go, right? So you're just, actually you're not always higher, but certainly for the HCN solid, you got 1.43. You said 1.39. That's a substantial difference, right? So is it that, and your work shows a higher density. Yeah, so I think that you're just making better crystals. You're making more appropriately crystals.
Yeah, I don't.
B came from our laboratory.
Yeah, here is our co-author here.
I see. Okay, all right. So maybe this is politically challenging to come up with a different number.
So the 1.39 in the middle of the slide there, that actually came from this laboratory. And I think part of it is due to the fact that we're a lot smarter than we were 10 years ago about some of these things.
Okay, good.
That's I hate to admit it, but that's probably what it is. It's just that we're much better about measuring things.
Oh, so you don't think it's the quality of the crystalline material that you're generating?
It may well be the quality of crystal material. It might just be that we're better at growing this stuff now.
Yeah.
Slow down the purity of the compounds. We're using a little bit better vacuum system now, but 1.43, 1.39, that could well be the better crystal.
Yeah.
And better genetics.
Good. Thank you very much.
Thanks, David, for the question.
All right, so I think we will have to move on now. I thank Yuki for a very nice talk. I'm sure many others are thanking you too. So we're going to move on to our next speaker now. Our next speaker is Professor Ralph Kaiser. I'm going to start introducing him while we switch to his presentation. Okay. Professor Ralph Kaiser did his diploma and his PhD from University of Münster in chemistry. And after that, he did his one postdoc at University of California, Berkeley in reaction dynamics from 94 to 97. And then he spent some time in Academia Sinica in Taiwan. Then he did his habilitation in physics from 97 to 2002. And since 2002, Professor Kaiser has been in University of Hawaii and is currently the director of W.M. Keck Research Laboratory in astrochemistry. Ralph has won many prizes, including the ACS Fellow and many others. I'm not going to give a list of that here. He has been the chair, is a past chair of the astrochemistry subdivision and one of the first founding members of the astrochemistry subdivision for ACS. Today, Professor Kaiser is going to talk about an aromatic universe, a physical chemist's perspective. So take it away, Ralph.
Okay, thanks very much, Partha. Can you see the screen?
Yes, we can.
Oh, perfect. Thank you very much for the possibility to present some of our results we investigated over the last years on the formation of aromatic hydrocarbons in gas phase and also in the solid state. So polycyclic aromatic hydrocarbons have been very important, and they have been detected for at least 20 years in meteorites, for example, such as the Murchison meteorite. The most important issue is that these polycyclic aromatic hydrocarbons have carbon 13 and carbon 12, very important. Hello? Hello, I cannot see. Hello? Hello?
Everything seems fine. I think you should be good to continue.
Sorry, there seems to be, we can't hear Ralph, but we can see Yuki. Yuki, can you switch off your camera?
Ralph has disconnected.
Oh.
Okay, okay. Now we can, what should we do to
we can give
fill
him, we can give him a minute to see if he reconnects. You can email him.
Yeah. Yeah. Sure, he's trying. Let me just try and. Sorry about this.